yours.
Thank you, Hans. Good afternoon, everyone. Let me just briefly introduce myself. I'm full professor here at the University of Karlsruhe, which is now called the Karlsruhe Institute of Technology. I have a chair and a professorship for hybrid and electric vehicles, HEV. I'm doing this since about 10 years, and in my previous life, I was with the industry, and most basically, I'm a designer, engineer of electric machines, electric motors. I've been working in that field for many, many years. Also, I'm involved in standardization. Today is about electric vehicles and the famous or infamous argument of marginal emissions. Before I start with that specific topic, I would like to draw your attention on the growth of electric vehicles and the electric car fleet in the last 5 years. The figures that you see here are probably very well known. They're from the CSV, which is a German institution that is also associated with my institute, with the Karlsruhe Institute of Technology. And they always estimate the total figures for battery electric and plug-in hybrid vehicles at the end of each year. And the latest figures obviously are from the end of 2020. You can see that there are around about 5 million electric vehicles in China, another 2 million in the United States, and then you can see the list for yourself. At this point in time, we're nearing the end of 2021. I would assume we're already somewhere around 12 or probably 13 million electric vehicles in the world. And so this whole thing is a success story, and we'll come back a little bit later on the adoption rate and the growth and the prospective, the likely outcome in the next couple of years. One big discussion when it comes to electric vehicles is always the question, well, are electric vehicles actually more CO2 emission friendly than combustion engine cars or other sorts of alternative fuels? And one of the factors that comes up when we talk about CO2 emissions is always the CO2 emissions that are arising from the battery. Because as you're certainly aware, batteries need to be built with raw material, need to be built with a lot of energy that takes or produces a lot of CO2 emissions. And one interesting aspect that is not so very well known in the public is that batteries are getting better all of the time. Not only are they becoming cheaper, but also the use of raw material and the use of energy per kilowatt hour is going down. What you can see here in this chart is basically the development we had during the last, let's say, roughly 10 years. This is the watt hours per kilogram, or simply said, the energy density. And the higher the energy density, the less material and energy you need to build batteries for the same capacity. What you can see here is that we have increased the battery energy density from round about 140 watt hours per kilogram per cell in 2012 to 240, 250 watt hours per kilogram per cell in 2018, 2019. So it's almost doubled. Or in other words, the backpack has almost halved in that time. But that's not all. The development is continuing. Basically, there are 3 developments that are ongoing right now. First thing, of course, is we take the battery technology that we have today and improve it. So we stay with the NCM, nickel, cobalt, mangan cathode. We stay with graphite anode, but we add a little more silicon to the anode and improve also the cathode material. And that will lead us in the next coming years to round about somewhere like 300 watt hours per kilogram. By the way, these figures here are now taken from a presentation of the company SVolt, which is one of the smaller of the large Chinese battery manufacturers. And it's from the presentation they gave 1 year ago. The other companies, however, are on a similar path. So that's one direction, further development of the state of the art. The next direction is LFP batteries, lithium iron phosphate. Well, as you can see, lithium iron phosphate batteries have a much lower energy density. So you could think, well, that's not a progress, that's a step backwards. Yes, in some ways it is a step backwards. So you need more battery material, but the big advantage is you need less copper. You need less carbon, not copper. Copper is not a very significant element in the batteries. You need less carbon. Cobalt is the word, I'm sorry. Need less cobalt. And cobalt is a very difficult material, as you know. It's only found in very few places in the world. It's very costly, and there is a lot of concern about the mining of cobalt. And so LFP batteries have a big advantage because they use less cobalt. Also, LFP batteries are pretty cheap, also due to the fact that they use less cobalt, and they're very robust. They can be charged very quickly, they can be discharged very quickly, they have a very long lifetime. They're almost impossible to burn, so there's a lot of benefits. Today, you can already get cars with LFP batteries. Tesla has announced and is already delivering cars with LFP batteries. However, only they're short-range cars because the energy density is not good enough. In the future, we will see LFP batteries more and more coming up, also in buses, in trucks, and trains, and other applications, but not so much in cars, maybe in city cars, short-range cars. And then there's a third trend, and the third trend is, of course, the new solid-state batteries, high-performance batteries that build up on the batteries we have today, but replace the liquid electrolyte with a solid electrolyte. And that battery technology will then, over time, enable us to increase the energy density even further. And the discussion is now that we think energy density will be able to grow up to 500 watt-hours per kilogram in the next coming, let's say, 5 to 10 years, broadly speaking. That would be another doubling of energy density. And that means that at the same weight and the same total carbon emissions, we would have double the distance, the driving range, or if we keep the driving range as it is today, by the way, I think it's more than enough, but that's another discussion. If we keep the driving range, go to the new battery technology, we will halve our CO2 backpack. So there's a lot of interesting things going on in this regard. The development and current trends I see in electric vehicles are basically two. First, more range. Increase in range even further. The car you see on the top left, the NIO ET7 was already announced, I think this year. It was displayed at the Munich car fair. And it is announced that this car is coming out next year and will have a solid-state battery for the first time. Also, you can see the Daimler EQS in the upper right-hand corner. Of course, these are just examples. That's a car that has a 120 kilowatt-hour battery and 707 kilometers of announced range. This car you can already buy. By the way, this is tested according to the WLTP cycle, while the other is tested according to the new European driving cycle. So effectively, the real driving range of both cars should be quite similar. So that's one trend. And the other trend would be more affordable cars. Battery electric vehicles are getting cheaper and cheaper all of the time. And that is a trend that I would assume is going to continue for some time in the future. You can see here on the lower left, just one example of a very cheap car. And after incentives, you can buy this car for around about 10,000 euros, depending on the country where you live and the incentives that you get. 10,000 euros for a brand new car, full electric, battery electric vehicle. And the lower right, you see another example of a pretty big family car. And again, this car is, before incentives, is only 36,000 euros. And after incentives, well, depending on the country, between 25 and 30,000. Now, let's look at marginal costs, shall we? What is the argument about marginal costs? Basically, the argument is as follows. Renewable energy is in very limited supply in most countries, which is certainly true. And the renewable energy is fully used by the existing customers. So when you plug in a new electric car, the only option to get the electricity, the additional electricity for that newly plugged in car, must come from coal-fired power plants. And so you have to calculate the carbon footprint of electric cars only exclusively with the emission factor of coal-fired power plants. And as a consequence of this great argument, it would be much more environmentally friendly just to stick with internal combustion engine vehicles. And well, of course, they are getting better all the time, continuously getting better. And so we can just forget about electric cars and just go on as we did in the past. That's basically the argument of marginal costs. And for a very long time, I thought this was a stupid argument. By the way, I still believe it's a stupid argument. And nobody would honestly bring this forward outside of, let's say, some friendly, direct discussions. But I've recently learned that there even is a pseudo-scientific article that has been published in a magazine, and a peer-reviewed magazine, by the way, that's hooking onto this marginal cost argument. So let's talk about how to understand this argument. And one of the main things in this argument is the very last one. It would be much more environmentally friendly just to stick with the internal combustion engine, because the combustion engine cars are getting better all the time. Is that really true? Let's look at reality. First, I show you the picture and the data of the emissions according to the new European driving cycle, according to manufacturer data. This is what the sticker on the cars is showing. And I'm sorry, but these are all numbers from Germany and German car manufacturers. And what you can see is in the last, let's say, 15 years, the NEDC emissions that have been displayed on the label of the cars was going down all the time, from 7.3 liters to 5.6 liters in case of gasoline engines, and 6.5 to 4.8 in case of diesel engines. But you can also see that since 5 years, the numbers are stalling. They're not improving anymore. Actually, they're going up. The very last numbers for 2019 are changed due to the WLTP cycle and not using the NEDC cycle anymore. But before, you can even see from 2015, 16, 17, 18 that the numbers are still are actually going up. But this is, of course, only a part of the picture. This is what the manufacturers claim their cars are consuming. This is not the real deal. This is not what they're actually consuming. Let's look now at the figures, what the cars are actually consuming. These are actual fleet emissions. They are based on data of total driving distance and total, that means annual fuel consumption. And these figures, this data, is coming from the German authorities. That means Kraftfahrtbundesamt, who is familiar with German authorities. So what they are looking at is just how much gasoline and how much diesel is sold per year, because the fueling stations have to pay taxes. That's very well known. And also, what is the total driving distance of cars? That's also quite well known, because cars have to go regular service maintenance inspections. So we know quite well how far cars are driving. And what you can see here, first of all, of course, these figures are much higher than the figures we saw before. Secondly, they are not dropping at all. And thirdly, actually, they are increasing. And they're increasing for more than 10 years, or around about 10 years. So coming back to the argument of marginal cost, just waiting for combustion engine cars to become better will never get us anywhere. That is obviously not an option. But coming back to the marginal cost argument as such, and I will give you some reasons why these arguments don't apply to electric cars. First of all, what is marginal costs? Marginal costs is cost, or is a method to compare alternatives that lead to the same goal. For example, if I have a plant and I'm producing some sort of things, let's say I'm producing vacuum cleaners in my plant, and I want to increase the outcome of my production. I want to just produce more vacuum cleaners because I see there is a larger market and I can sell more if I produce more. I have several options of increasing the output of my plant. For example, I could just hire more people and make those more people work harder and produce more vacuum cleaners. That's one option. Or I could increase the level of automation. I could just add more robots, more production facilities in my plant and increase the output this way. And then I can compare the costs associated with each and every option. And then I can say, how much is this going to cost me? How much is that going to cost me? And I can take my decision. But the point here is, at the end, we always have the same goal. In our case, coming back to cars, the same goal would be reducing CO2 emissions. The problem is, as we've seen before, we have no alternative to electric cars. Few cars will always be dirty, and they're not getting any better, as we've seen before. So the whole marginal cost argument doesn't apply. Second point, marginal costs are used to compare alternatives, but they do not reflect the actual costs after the fact. When coming back to the argument of the power of the plant that's producing vacuum cleaners, when you have made the decision how you will change your plant to increase the production, then you will make a new calculation of the production costs and of the costs that your vacuum cleaners are going to cost you. But of course, you will not make a difference between the vacuum cleaners that are produced the old way and the vacuum cleaners that are produced the new way. You will have just one cost calculation for all the vacuum cleaners that are coming out of the renewed factory. Electric cars use the same electricity as every other consumer. And we can even go one step further. And if we say the argument new electric cars take only coal-powered electricity is true, then we must apply the same argument to all new electric appliances, not just to new electric cars. So we must say, okay, if I buy a new refrigerator, if I buy a new oven, if I buy a new television, if I buy a new heat pump, these appliances also are added to the grid and also must be calculated with coal power plant emissions. Actually, each and every consumer of electric energy that is currently on the grid has been added to the grid at some point in the past. So if we take this argument to its extreme, we must say that we have to calculate each and every consumer with coal power plant CO2 emissions, which is obviously nonsense. There's even more. Electric vehicles are not only consuming energy and are a burden, but they can actually help. They can help the grid to improve. They can be scheduled to run at times of high renewable electricity generation and low overall demand, for example, before peak hours or during the day or in windy nights. This flexibility can then be used to help integrate an increasing share of renewable energy, and that improves or provides an opportunity to deploy renewable energy faster and further. So if it's done in the right way, if we give incentives for people to charge their electric vehicles at the right point in time, then we can actually support the grid. And we can also support the grid by having two-way charging, meaning that the electric cars can also stabilize the grid when they are connected and they don't need to drive. And finally, historically, if we look at the additional demand that is generated from electric vehicles, that has always been much smaller than the increase in renewable energy generation. So in other words, the CO2 emission factor has been improving all the time, even though we have added electric vehicles, because we have increased the renewable energy production much faster than we have added new electric vehicle consumption. For that, I have also some figures here. This is, I'm sorry, again from Germany, but I have some European figures on the next slides. What you can see here is over the years, the total electricity production in Germany, beginning in 2002. And you can see also here the green bars, that's renewables, and the red bars, that's non-regenerative sources. And you can see how this is climbing, how the part and the share of renewables is climbing. We're now round about at more than 50% of renewable electricity production in Germany. At the same time, you can see this blue line, and that blue line is the emission factor, the CO2 emission factor. And since many years, this line is basically falling down. Since 10 years, it's continuously falling, and before we had two dips here, but it's going down and down and down. Going down means the CO2 emission factor is improving all the time. And if we extrapolate to the year 2050, adding the demand in that particular case of 48 million electric vehicles, assuming that all combustion engine cars in Germany are being transferred to electric cars during the next 30 years, then we end up at an electricity production or demand of somewhere here, 650 billion kilowatt hours or terawatt hours. And you can see that just by increasing the regenerative energy production at the same rate that we did in the past during the last 20 years, we will reach the goal. I'm not saying this is easy. I'm not saying this is necessarily cheap, but I'm saying it can be done. It is not a goal that is out of reach and out of discussion or whatever. It is a goal that is quite realistic to do this. Now let's look at Europe. Let's look at the European power production. And here we can see, again, the data from the last 20 years. And this is basically all of Europe, excluding Russia, Turkey, Georgia, Armenia, and Azerbaijan. And you can see that the renewable energies have more than doubled their share of the European power generation in this century. And it's by far more than we have added demand from electric vehicles. More interesting is the outlook, the European outlook. This is the combined capacity of all power plants planned and under construction in Europe in megawatt. And that's pretty recent. That's coming from Energy Monitor just a few weeks and months ago. In 2020, there was 27 gigawatts of new renewable generation from solar and wind power in the grid in Europe. And this exceeds the increase in electricity demand from the EVs and the heat pumps by far. In 2020, the EU generated 73 terawatt hours more renewable electricity than the year before. Now let's put this rather stupid argument of marginal costs and electricity production and electric vehicles to side, and let's look at the life cycle analysis of cars. Obviously, this is a field where you can do a seminar on its own. So I've just brought one slide with the most recent data. This is assuming a mid-sized car in Germany. I have more on European comparisons on the next slide. And you can see the life cycle CO2 emissions in equivalent CO2 emissions per ton per vehicle over the 160,000 kilometers. And it's calculated for diesel, for gasoline, which is basically the same. And then you can see this is this line here, and then you can see the current backpack of the battery, which is here. And then you see the line, this line up here is for the German grid, if the battery electric vehicle is charged from in German grid. And remember, Norway, Switzerland, and other countries in Europe have much better power factors, CO2 emission factors than Germany. And this would be a situation where the owner of the car has its own photovoltaic, its own local photovoltaic, and it utilizes the photovoltaic with a share of 50-50. So meaning that 50% of the charging takes place from the self-produced energy, 50% takes place from the grid, which is quite typical for photovoltaic systems. And you can see that in this case, you can save even more energy. Roughly speaking, you can halve the CO2 footprint of the car. Now, let's look at the European situation. This is a comparison that I've taken from this website down here, Fact Check. And you can see the comparison of an average mid-sized car, just like the one I did before. In particular, this was a Tesla Model 3. And they've compared it to conventional vehicles. What you see here, an average European car. And this time it's the grams per kilometer, but it's also CO2 equivalent emissions. Over 150,000 kilometers total lifetime, including the backpack for the battery and the production of the car, not including second life, not including recycling, which is also not included in my calculations. That will make the situation much better for electric cars, by the way. And you can see in this case, the conventional car is somewhere around 260 grams per kilometer. And then the electric car is depending on where you plug it in. In Germany, it's rather bad, somewhere here with a certain range of uncertainty. In France, with all the atomic power, it's down here. Norway, with all the water power, it's down here. And the EU average is somewhere here. And by the way, these bars come from the battery production. If the battery production is in Asia, it's rather the upper end. If the battery production, in this case, was done at the Nevada factory of Tesla, which is completely solar powered, then this bar would be at the lower end. So we actually have this amount of CO2 emissions. Even if you compare this Tesla Model 3, which is a relatively large car, to a very small, very, very efficient, probably one of the most efficient combustion engine cars that you can buy today, the Toyota Prius, which is, again, a much smaller car and a hybrid car, and probably the best you can do, you can see that even then, with some very few exceptions, the Tesla Model 3 is much better. And that's not typical for Tesla only, it's for all electric mid-sized cars. They are much better than even the best you can do in combustion engine cars, even though this car is a lot smaller. My last discussion point today and my last input for this webinar today is about the adoption of new technology. This is a picture I took from a presentation of Tony Sieber, and I think he himself took it from another presentation, but I've given you the reference down there. And I actually like this graph quite a lot because I think it's very revealing. You can see the adoption rate of different new technologies over the last more than 100 years, starting with the telephone, ending with social media, smartphones, and tablet computers. And basically what you see there is that you have an S-shaped curve. You see that for a long time, not so much is happening. Then there is a certain tipping point. And when that tipping point, which is around about 10% market share, when that tipping point has reached, the development of the adoption is very, very fast. And then at the end, of course, the last remaining 10%, there are always the doubtful customers that never buy anything that's newer than 20 years. And they're difficult to convince, but that's probably not so important. And the big question, of course, is today, will this also happen to electric vehicles? I'm pretty convinced it will. And then the second question is, where are we on this line? Are we already after the tipping point? Well, to figure this out, I've brought you some data from new car sales in Norway from August 2021, so just a few months ago. And you can see that in Norway, roughly 3 out of 4 newly purchased cars are battery electric vehicles. And if you add the share of plug-in hybrids, you come to more than 90%. 9 out of 10 cars are battery cars. The share of combustion engine cars is only 7%, with 4% gasoline and 3% diesel cars. Less than 1 out of 10 cars is a pure gasoline car in Norway. So they are clearly on this steep incline of this adoption rate curve. In Germany, the situation is not yet there. Our situation in August was 15% pure battery electric cars and another 13% plug-in hybrids. But you can see even in Germany, we are nearing 30% of the cars that have a plug and run as electric cars in one way or another. So my personal guess is that even in Germany, we are now beyond the tipping point. Let me close the seminar by asking the question, what is the situation in countries that still have a very high CO2 emission factor, like, for example, Poland or China? Should they, or India, should they switch to electric cars now, or should they wait before their CO2 emission factor becomes better? My personal thinking is they should switch now for a number of reasons. First is electric cars immediately improve the quality of life. That means in city centers in particular, the noise emissions go down, the local emissions go down. Second argument, emissions from electric cars are constantly improving as the grid improves. So if you have the cars and your grid is bad now, but it's getting better over time, so will the cars. They will be getting better over time. Combustion engine cars remain the same all of their lifetime. Third argument, the conversion takes a long time, as we've seen. Obviously, electric cars and cars in general are relatively expensive compared to the monthly income of a typical family. So they cannot buy a new car every second month. So they have to wait before they can buy a new car. And so that takes time. And if we want to reach emission goals and we want to reach them quickly, then we must start now. And finally, I'm thoroughly convinced that electric cars will be wanted by the people anyhow. They are fun to drive, they are convenient, they are cheaper. Even today, the total cost of ownership of electric cars is already lower than most combustion engine cars. The upfront purchasing cost obviously is still higher. And so they are the future, and they are increasingly in demand, as we've seen also in Norway. Thank you very much for your interest. That was all I wanted to share with you today. I hope this was interesting to you. And now, as Hans said in the beginning, we have time for questions.